in this video I'm going to be demonstrating how we necessarily multiply complex numbers to get a new complex number. So basically, yes, if you multiply 2 or 3 or 4 or any number of complex numbers, you get some new complex number, and I just wanted to show how this is done. Now, typically if I was doing this in a class, I would actually derive a formula for doing this. I would say a plus bi times c plus di, given a, b, c, d are real numbers, and these are two complex numbers here. We'd actually take the time to FOIL this out. Basically, multiplication is carried out through processes of distribution. But it's a long derivation, and honestly nobody remembers the formula anyways. I think the most meaningful thing to do would be to look at some examples of just certainly how you would do this. I think, however, it is important to point out a few things, starting with this. Again, when you multiply two complex numbers, you should always get a complex number answer. So you're going to get some answer that can be written in standard form, a plus bi form. It must be able to do this. We say due to the property of the closure of the set of complex numbers, which I know you all wanted to hear. Also, the second thing I want to bring up is this. We need to be familiar again with the properties of our units of I, okay, or the imaginary unit. So whenever we see I, of course equals itself. But whenever you see an I squared, we're simply going to substitute in -1 because that'd be like saying I squared is the same thing as the square root of -1. Remember, that's what it equals, squared, which is just -1. Okay, so it's much more convenient to write a -1 in place of every I squared we see. As a matter of fact, get used to it. In this video, you're going to learn that wherever you see an I squared, you can just cross it out and change the sign of the number that it was attached to because it's a -1. Furthermore, we can say anytime we see an I cubed, we could replace that with -I, and anywhere we see an I to the fourth, well, that's just 1. The bottom line, though, is this. Higher powers of I always collapse back down to either positive or -1 or positive or I. It collapses back down. It never goes to higher power. So, yeah, let's go ahead and take a look at a few. Starting with this. So we have the complex number 4, and yes, the complex number 4. I say 4 because 4 can be expressed as 4 plus 0i, this 4 right here. I don't want to do that because it's kind of a lot of writing, but basically, yeah, it can be seen as written as 4 plus 0i, and it would work just fine. We could FOIL that. But in this case, it's much more convenient and concise to just say 4 times the complex number -2 plus 3i. In this case, we'll just go ahead and distribute, which you'll see a lot in this video, but we end up with -8 plus 12i. And if you're saying to yourself, that was pretty easy, then you are correct, because that's all we need to do. When we have our new complex number that can be written in standard form, and you notice that we basically just quadrupled the values. There's nothing wrong with this. Okay. So moving right along, letter B here, you're going to see that we have 2 minus I times the complex number 4 plus 3i. And as I mentioned before, we're going to need to FOIL here. So let's go ahead and FOIL this out, and I just want you to see what happens here, because you're going to notice we get some I squareds in here. We get an I squared, but we need to be able to write it in, standard form, which is a plus bi form. How can we do this when we have I squareds and there's no I squared up here? So let's go ahead and take a look at this. So if we FOIL this out, multiply the real parts, we end up with 8, okay? So 2 times now our, positive 3i, we get positive 6i. -I times 4 is minus 4i. And then -I times a positive 3i is -3i squared. Now again, I need us to recall that this I squared is the same thing as -1. Often we see that probably more than any of these other, 3 up here, I cubed, I to the fourth, or just I. But check it out. So when we see this I squared, we can actually rewrite this as 8. Let's go ahead and combine like terms here. We have a positive 6i and a -4i. Combined to be positive 2i, and then we have -3 times I squared, which is -1. So when we go ahead and take this -3 now times this -1, we end up with a positive 3. This is a lot of writing. I usually don't do this much. I just do a lot in my head, but you get used to it. So plus 3, and then now we see that this 8 and this 3 can be combined. We end up with a grand total of, it seems, 11 plus 2i, and you'll notice that this was entirely able to be written in standard form. So yeah, FOIL, just get used to it. I squared is -1. That being said, hey, example C here. Now, if you're taking notes or you're doing anything with this, really write down example C, because what you'll notice here is this. One of the complex numbers is 3 plus 2i, and the other one I've written down as 3 minus 2i. And I've done this on purpose. As a matter of fact, we might recognize that this will multiply out to be a difference of two squares. That's kind of key here. And also this, we say given a complex number a plus bi, then its conjugate, okay, its conjugate pair is a minus bi. And the interesting thing is when you multiply two conjugates, of course we said it comes out to be a difference of two squares, what you'll find out is this. A complex number multiplied by its conjugate, really what happens is you get like a squared, and then you get minus abi, but then you turn right around and you get plus abi. So those middle terms always just kick out. And then you have this negative bi and positive bi, so you get negative b squared, I squared. So in other words, this I squared, recall I squared, yeah, well that was the same thing as negative 1. So this all boils down to every time a squared plus b squared, okay? And that's the nice thing about complex numbers because our I always cancels out. So we'll see this in action here, but we love multiplying by conjugate pairs because it eliminates any i's in the problem. Of course, we kicked out the middle i's, and this I squared is going to go away just by default because it's a negative 1. So let's go and take a look at what this looks like when we do this. I'm going to switch over to green here for this one. So we say 9, which is our 3 squared, our first thing squared, like over here, like this, okay? 9, and we say, okay, so now 3 times negative 2i is negative 6i. We turn right around and get a positive 6i, multiplying those by definition there, and we say, okay, so, and then we have 2i times negative 2i, so it's negative 4i squared, or we could even say, minus 2 squared I squared, kind of like when we were over here. Now recall that because one of these is positive and one of these is negative, when we do our last multiplication here, we always get a difference. But then we turn right around and say, well, hey, you know what, I squared, what we know about that? Sorry, we'll do that in red. We get this, we get 9 minus 4 times negative 1. Really, which converts that back to 9 plus positive 4, okay? So we get 13. And so the cool thing, I just want to iterate this again, is when you multiply two complex numbers that are conjugates of one another, that is if one's a plus bi, the other one's a minus bi, same numbers, just two different signs, you end up with something that is purely real in the end. And that comes into play in some further videos when we're trying to eliminate i's from an expression. Okay, so cool, remember that. So what about this here? And I could write this a little bit better. This is 3 plus 2i quantity squared. Now, what you'll notice is this, you know, a lot of people try to tell me hey, don't do this. This is not 3 plus 2i squared. You don't distribute exponents. No, this is bad. This means 3 plus 2i times itself. And in this instance, yes, it's kind of like the last example over here. But one's not plus and another one minus. These are both plus, or maybe these were both minus. What you're going to notice is the middle term doesn't cancel out this time. So let's go ahead and do our FOIL. We get 3 times 3 is 9. 3 times positive 2i, so there's our 6i that we got kind of like last time. But again, this time they don't cancel out because we get another positive 6i, and then we end up with plus 4i squared. So a few things we need to say about this. First of all, we need to write our answers in standard form, a plus bi form. And you might be saying, oh, well, I got an I squared here. That's kind of not good. But I'll tell you what. We'll go ahead and bring down our 9. Excuse me. These two positive 6i's combined to become 12 total i's. And then we have, of course, 4 times I squared. But what do you know about I squared? Okay, remember, I squared is always just a negative 1. So this expression simplifies into 9 plus 12 i's minus 4. And so now we can combine like terms here. Our positive 9 and our negative 4 combine to produce a real part of this number of 5 and an imaginary part of 12i. And so we say, okay, so here is our complex product, or the product of the number 3 plus 2i with the number 3 plus 2i. We get 5 plus 12i. Bottom line is, a few things I want you to pick up from this video. every product of two complex numbers must turn out to be a complex number that can be written in standard form. If you're saying, how does this come out to be standard form? Okay, it has to be able to be done. So just keep searching for a way. And also this, when you multiply two complex conjugates, man, if you're watching this just for fun, hey, good for you, because I don't think my videos are that entertaining, honestly. But when you multiply two complex conjugates, okay, write this down in your notes if you're taking notes. Bottom line is this, you always get a squared plus b squared, whatever this is, due to the fact that you end up canceling out your middle terms, and the last term, which was a difference, it was usually a difference of two squares, that I squared pops our negative or minus b squared I squared back to a positive b squared. Okay, this is always the case.